In this video, I want to talk a little bit about high-pass filters and why they respond the way they do. Here you can see we have an input voltage to a low-pass filter, which is a square wave. It goes up to 1 volt and then down to -1 volt, up to 1 volt and then down to -1 volt. The output voltage in comparison goes from 0 to 2 volts down to 0, and then from 0 to -2 volts and back to 0. So I want to see if we can understand this phenomenon. And so in order to do that, I'd like to start by reminding you that a capacitor voltage can never change instantaneously. That's sort of the key to understanding this. For a capacitor voltage to change instantaneously, that is, for a capacitor voltage to have a discontinuity, then that would mean that dV/dt would be infinite, which would mean that you would need an infinite current to make that happen, which is impossible. So we're going to remember that cap voltages can't change instantaneously. So let's start our analysis by assuming that the input voltage is at 1 volt and the output voltage is at 0. So I'm going to write those numbers down. The input voltage is at 1 volt. The output voltage is at 0 volts. So in that instant, when the circuit is as such, then the capacitor voltage is equal to the input voltage of 1 volt minus the output voltage of 0 volts, which gives me 1 volt across the capacitor. Now, right when I get to this edge, the input voltage is going to drop from 1 volt to -1 volt. So let's see what happens when that happens. So right when that occurs, the input voltage will switch instantaneously, but what we've just learned is that the capacitor voltage cannot change instantaneously. So if it's equal to 1 volt just before the input switch, it's going to still equal 1 volt after the input voltage switch, because it can't change instantaneously. There will still be 1 volt across the capacitor. However, the input voltage has switched instantaneously. That is now -1 volt. Well, the only way for that to happen is if the voltage across the resistor equals -2 volts. If the voltage across the resistor is -2 volts, that will work. And that's why we see the output voltage drop to -2 and then back up to 0. So you can see the output voltage went to -2 volts and then eventually decayed back to 0. And the reason it decays back to 0 is that once the switch has been made, eventually the cap is going to open again, it's going to charge and become an open circuit. And when it becomes an open circuit, the output decays back down to, that's how it means the output has decayed down to 0. Okay? So once the output decays back to 0, and I want to mark this was -2 volts. So now let's see what our status is. Now our status is a little bit different. The input is now -1 volt. The output voltage is 0 volts because it's 0 volts. And oh, you know what? I drew my line incorrectly. I beg your pardon. This 0 is here, so it should have looked like that. That's a little bit more accurate. Okay, so that's my 0 volts. That's my -1, and that's my -2. Okay, so now what's our status? The input voltage is still -1. The output voltage is 0, which means the voltage across the cap is now -1 volts. In the instant before my input voltage switches back up, the capacitor has -1 volts across it, which means that in the instant after the capacitor switches, in the instant after the input voltage switches back up, I still have -1 volts across the capacitor. Now, how can that be? Well, the only way that I can still have -1 volts across the capacitor is, let's see, my input voltage is now 1 volt. Oops, I cannot write apparently. My input voltage is now 1 volt minus V sub R, the voltage across the resistor. Well, the only way to make that happen is if V sub R equals 2 volts. Okay, that's the output voltage, is the voltage across the resistor. So what we're seeing now is that the output voltage will now jump to 2 volts. All right. And then once again, once it's done that, it will start to discharge. Sorry, the cap will start to charge, which means it'll start to become an open circuit. And as it becomes an open circuit, eventually the output will decay back to 0. All right. And once it's done that, now it's wash, rinse, repeat. Every time the input voltage switches, the output will just repeat the process. Okay? So that's where that comes from. Now what's really interesting about this is that it seems that what's driving the output voltage is the change in the input voltage. And look how interesting this is. What if we try the process again, but let's have our input, instead of swinging from between -1 and 1, what if it swings between 5 and 3 volts? So let's have it go 5, 3, 5, 3. Okay, so 5, 3, 5, 3 volts, which is basically the exact same thing that we've just dealt with, but with but now we have a DC offset. So let's go through the steps again and see what happens. I'm going to redraw my circuit just for convenience. There's the capacitor, there's the resistor, there's the output. Sorry, there's the ground, and this is the output. So let's say now that my input voltage is 5 volts. The capacitor is an open, which means that my output is 0 volts. So in this moment, the voltage across the capacitor is 5 minus 0, which is 5 volts. And then I'll make the transition down from 5 volts to 3 volts on the input. And as we've just been discussing, in the instant before and after that corner, the capacitor voltage will have to remain constant at 5 volts because it can't change instantaneously. Well, how can we make that happen? The input is now 3 volts, which means the only way to make that happen is for the voltage across the resistor to equal, wait for it, minus 2 volts. So my output voltage was at 0, and then it went down to negative 2 volts. And now that it's at negative 2 volts, the capacitor is going to start to charge, meaning that it's going to start to become an open circuit, and eventually it will become a completely open circuit, and the output will be back at 0. So what do we have in that case? So now we're here. The voltage across the cap is going to be equal to the voltage at the input, which is 3, minus the voltage across the resistor, which is 0. So there's 3 volts across the cap. Right here, there's 3 volts across the cap. And as soon as the input makes it switch, we will still have 3 volts across the cap. Well, how can we make that work? How can we get 3 volts across the cap? Well, the input is 5 volts minus the voltage across the resistor, because that's the equation for the cap voltage. Well, the only way to make that work is if V sub R equals 2 volts. So now that's going to go up to 2 volts, and then that's going to decay back down to 0. Okay, down, up. So what it seems that, and this is the exact same as before. Same as before. Which is cool, because what that's telling us is that the DC offset has no impact. So DC offset didn't change the output. Because look, the only difference between case A and case B, those are the exact same input signals except with 4 volts of DC offset between them. And it turns out that 4 volts of DC offset didn't make a difference. It didn't change the output. And that makes sense. We expect that because DC offset is by definition a 0 hertz signal, which is a low frequency signal which gets rejected by the high pass filter. Therefore, if you add a 0 hertz signal to the a 0 hertz component to the signal, that's not going to change the output at all because it's low frequency. It's getting filtered away. It's getting removed. So adding a DC offset won't change the output. And that's actually correct, right? We can prove that with our circuit intuition. We can prove that with our signals intuition. And if we go back to the actual circuit that we're looking at, we can see that if we start to change the DC offset, let's say I decide to add a volt of offset, you can see that the output didn't change. All right, no matter what I do with my DC offset to the input, the output's going to stay exactly the same. It doesn't matter. So I hope this explains a little bit in more detail how the high-pass filter operates. I thought this was pretty cool, and I hope you do too.